The topic for today is equilibrium of non-concurrent force systems. This was a topic for Module 1, but since we ran out of time, I'm going to discuss it here on Module 2. Okay. So, as usual, we'll have an introduction, a short one, because equilibrium of non-concurrent force systems is just the combination of equilibrium of concurrent and parallel force systems, which means we're going to use equations, summation of Fx equals 0, Fy equals 0, and Mo equals 0, or moment equals 0. Okay, so that's it. All the concepts previously discussed are applied here. So now let's have a few examples to better understand equilibrium of non-concurrent force systems. Let's start with number 1. Let me first fix the setup. Okay, number 1. I'm gonna answer number 1 on my own. You just have to listen for now. So a boom AB, this is your boom, supported in a horizontal position by a hinge at A and a cable which runs from C over a small pulley at B as shown in the figure. So this boom is supported here at point A as well as by this string to this pulley B. Compute the tension T in the cable and the horizontal and vertical components of the reaction at A. Neglect the size of the pulley at B. So basically, we're looking for tension and then horizontal and vertical components of your reaction at this support. Let's begin. So when you have this, okay, this can be redrawn into this, okay? So we have a support here, which will experience reactions, okay? So let's call that, this is guessing the direction of your reactions. So I'm gonna guess there's an upward reaction here at A. We'll call that AV for vertical reaction. And then, remember this is a pin support. A pin support has horizontal and vertical reactions. So there's also a horizontal reaction here. Again, I'm guessing the direction, and then we'll call this AH. Okay? And then we have external forces here. 200 pounds. And then we have another one here, 100 pounds. And then, okay, at this point C, there's a cable. Now remember, whenever you have a pulley, the force on one end of the cable is the same as the force on the other. So meaning, if this is P, if I cut the cable here, the force will also be P. Okay? So that means, since the free body diagram that I'm drawing is the boom, all I need is to draw the forces acting on it. So I don't have to draw this pulley, I just have to draw a cable connected to this boom. Okay? And then this is a cable that's always carrying a tensile force, which is always outward. So this is your T. Okay? And then look here, right? This string has these dimensions. So base 4, height 8. So meaning, I can figure out the slope of this cable, which is also the slope of this force. Okay, so again, base 4, height 8. So this is 4, 8. Or you can simplify, divide everything by 4. 4 divided by 4, that's 1. 8 divided by 4, that's 2. And then compute for the hypotenuse, square root of 1 squared plus 2 squared, that's square root of 5. Okay, so now this has the same slope, 1, 2, square root of 5. Okay, and then don't forget the dimensions. This is 2 feet each. So 2, 2, 2. And now you have your free body diagram. So you can use your equilibrium equations to solve for the unknown. Once again, equilibrium equations are your summation of forces equals 0 and summation of moment equals 0. Now, usually, whenever we're solving for reactions at a support, the first equation that we'll use is moment. Okay. Now, and the problem here is there's only one support, which is here. If there was a roller here, right, I can use summation of moment at this roller to get AB. But since we don't have that, there's no problem there. We can still choose summation of moment at this point to get the value of T, your tension. Okay. So let me just indicate this is A, B, C. Okay. Again, let's begin with moment, specifically summation of moment at A. So equals 0. AV and AH passes through A, so ignoring that. Next, we have 200. That's clockwise, therefore positive 200. Perpendicular distance is 2 feet. Next, T. Now, when I extend the line of action of T, this is the perpendicular distance. And I don't want to solve for that. But however, since I'm given the slope, I can just solve for the components of T. Okay? So let's do that. So this is Ty, and then this is Tx. Tx passes through A as well. So ignoring that, we're left with Ty, rotate about A. That's counterclockwise, so negative Ty. And Ty is the y component of your tension. And to get the y component, that's just T multiplied by the vertical side over its hypotenuse. So T times 2 over square root of 5. Next, get the perpendicular distance, that's 4 feet times 4. And then lastly, your 100-pound force, that's also that's clockwise, so positive 100, total distance 6. Okay, and then from this, I can solve for T, which is 279.51 pounds. Okay, so that's the first answer. Next, I have to find out the reactions AV and AH. So that's easy. Now we're gonna use summation of forces. So let's start with summation of forces vertical equals, wait, let me move things around. Yeah. Okay. So now summation of forces. We can start with either vertical or horizontal. So let's try vertical or y. Summation of forces y equals 0. So let's start at the left side. AV is upward, therefore positive AV. 200 downward, so negative 200. Ty is upward, so positive Ty, which is again just T times 2 over square root of 5, considering T is this value. And then we have negative 100 equals 0. From this, I can now solve for AV, which is 50 pounds. Okay, and then finally, to solve for the horizontal component of the reaction, summation of forces H equals 0. So AH to the right, so positive AH. Next, we have this TX to the left. So TX is the horizontal component of T, so that's just T times horizontal side, which is 1, over hypotenuse square root of 5. Once again, T is 279. So from this, I can solve for AH, which is 125 pounds. Okay, and as you've noticed, all of my answers are positive, therefore all of the assumptions for directions are correct. Okay, so that's number 1. Any questions for number 1, please answer in the chat. Okay, great. So now let's move on to number 2. And then for number 2, I will take recitation. Okay. Okay. Number 2. Okay. So number 2, the frame shown in the figure is supported in pivots at A and B. A, B, similar to your guide mast in your previous lectures. Each member weighs 5 kilonewtons per meter. Compute the horizontal reaction at A and the horizontal and vertical components of the reaction at B. So we're looking for 3 things: reaction at A, horizontal reaction at A, and then horizontal and vertical reactions at B. Okay, so first thing to take note of is your weight. So each member, meaning member A, B, C, E, and FD or DF, carries 5 kilonewtons per meter. Now take note, that's not a point load, right? It's kilonewton per meter, so meaning that's a distributed load. So whenever you have a distributed load, you have to convert that to a point load. So if we were to draw that, okay, it's gonna look something like this. Okay, so downward force, and then we need to convert that to a point load. So here. Okay, so I don't have to draw that anymore. We can just compute for the point loads. Okay, so let's create a variable for each point load. So since all of these are rectangular forces or rectangular distributed loads, since it's area that's uniform, the position of your point load is going to be at the middle of your span. So for 6, the middle is at 3. Okay, so it's somewhere here. So let's call that weight 1 or weight of member CE. Next here, member AB, again, put that at the center. And this is your weight 2. And then, or weight, yeah, weight 2. And then here, again, still at the center, this is your weight 3. Then to get the values of that, remember it's just the area. Okay, so all of these loads are 5 kilonewton per meter. Since it's a rectangle, I just have to multiply that by the length of each member. So W1 is 5 kilonewton per meter, multiplied by total span is 6 meters, so that's 30 kilonewton, right? W2, okay, again, that's 5 times total length, so that's 3 plus 1.5 plus 1.5, that's 6. So 5 times 6 meters, that's again 30 kilonewtons. And finally, okay, so this is 5, and now I need to know what is the length of this. Now, if you've noticed, again, we have a right triangle here with dimensions 3 and 4. Okay, and whenever you have a right triangle with lengths 3 and 4 is the leg, it's easy to get, the length of this hypotenuse, and that is 5. Correct, Rafaela? It's 5. Okay, so this is 5 meters. Again, because it's 3, 4, 5 right triangle. Times 5, that's 25 kilonewtons. Okay, so now we have all of our loads. Next, it's time to use our equilibrium equations. Once again, we're looking for reactions that support A and B. So usually we're starting with moment. Okay. So let's try. Since we're only looking for AH here, okay, let's try to guess the direction of that. Okay, so I'm gonna guess it's to the right. Okay. So this is the reaction at A and AH. Now, by the way, there's no vertical reaction here, okay, because it's not supporting, or there's no vertical load upward. So meaning, yeah, cannot support, or there's no vertical force to support. While here at the bottom, okay, since it has weight, there's gonna be a vertical reaction here. So let's call that BB, and also a horizontal reaction, BH. Okay, again, this support does not carry, or there's no vertical reaction to support here, or vertical force to support here, since the weight is all downward. There's no upward force for this. All right, so that's why there's no reaction there. Next, choose a support to take your moment on. Okay, so I'm gonna choose point B, since first I want to know what AH is. So summation of moment at B equals 0. Let's start with AH, rotate about B, that's clockwise. So positive AH, perpendicular distance is 1.5 plus 3 plus 1.5, so that's 6. Next, W2 passes through B, so ignoring that. BH and BV both pass through B, so again, ignoring that. Next, W3, rotate clockwise, so positive W3, which is 25. Then how to get the perpendicular distance. This point load of your weight acts at the center. So meaning, if the base is a 4-meter span, this also acts at the center of that. Meaning, this distance is 2. Right? It's 2. Correct, Lauren. Okay. So that's why this perpendicular distance is also 2. And then next, W1, also clockwise. And then, as you can see, let's specify these distances. This is at the center. So this is 3 meters, 3 meters. Okay. So plus W1 times 3. And then don't forget the 200 kilonewton force. This is always downward. Weight is always downward, so rotate about B. Clockwise, so positive 200. And then perpendicular distance is, okay, this length, which is 6. Okay, please solve what's AH. Correct, Michelle and Nicolas. Oh, you're off by 1 number. So Michelle and Francisco, so Legado and Leon. It's negative 223.33. Again, negative is important because, or the sign is important because that tells us if our assumption is correct or not. So this is negative 223.33. Okay, you can store that in your calculator. And then take note of the final answer, the actual answer. Since this is negative, that means the assumption for this direction is incorrect. So AH is actually 223.33 kilonewton instead of to the right. It's actually to the left. Okay. Right. So now you have AH. Next goal is to get BH and BV. Okay. So same with our solution before to get BH. Yes, correct. It's same as AH because if you do summation of forces horizontal equals 0, you'll see that the only horizontal forces are AH and BH, all to the right. So positive AH plus BH equals 0. And since you're not changing the direction, you're still going to use the value that you got in the original answer, which is negative 223. So negative 223.33 plus BH equals 0. So BH is 223.33 kilonewton. Positive, therefore correct assumption of direction. It's to the right. Okay, so correct Gian and Lawrence, which you have. Okay. Finally, okay, please wait for me to ask a question before you answer so that it's easier to take note. And then finally, summation of forces vertical to get BV. Okay, so let's start from the left-hand side. Okay, so we have BV upward, W2 downward. Okay, so positive BV minus W2 minus W1 minus W3 since they're all downward, and then minus 200 for their other forces. W1, BV, yeah, they're all downward. So equals 0. From this, please solve what's BV. Correct, it's 285. Positive. Correct, Lloyd and Gian. Sosa. Positive 285. Therefore, correct assumption for direction, it's upward. Okay? And that is how you solve number 2. Any questions for number 2? Please answer in the chat. Okay, great. Let's move on to number 3. Okay. Number 3. The truss shown in the figure is supported on roller at A and hinge at B. Solve for the components of the reactions. So straightforward, we're just solving for reactions at the support. Okay, so look at our supports. You have a roller here, and then a pin here. Recall, a roller only has one reaction, which is perpendicular to the surface. Okay, so therefore this is the surface. So perpendicular to that, we have this. Let's call that RA. Once again, there's only one reaction there. Then at a pin, we have two reactions, one perpendicular and one horizontal. So this is perpendicular. Let's call that BV since it's vertical. Again, we're guessing directions. And then I'm gonna guess my BH is to the left since I can see that I have an external force to the right. And remember, this entire thing should be in equilibrium. So meaning all of our forces should cancel out. Okay, so those are my reactions. Now you have to create your equations. Okay, so again, we're looking for reactions at support. We're going to start with moment. Okay, so you're going to choose whether at A or B. Doesn't matter. Okay, I'm going to choose B so that I can solve for RA. So summation of moment at B equals 0. Let's begin. 400, that's counterclockwise, so negative 400 times 12 times 3, that's 36. Next, RA, rotate clockwise, so positive RA times 12 times 12, 12 plus 12, that's 24. Next, your 240, pound force. Again, that's clockwise, so positive 240. Perpendicular distance from point B is this length, which is equal to 16 times 16. And then we have 600, rotate about B, that's negative, since counterclockwise. Perpendicular distance is 12. BH both passes through B, so ignoring that, equate to 0, please solve what's RA. Should be positive 740. Yeah. So correct Rafael and Sosa and Lloyd. So Sosa and Tabog. Okay. Again, it's positive 740. Meaning assumption for direction of reaction is correct. Unit pounds. So 740 pounds. Next. Let's check components of the reaction. So again, we're looking for the vertical and horizontal component reaction. So similar to what we did earlier, just gonna choose summation of forces, either horizontal or vertical. Let's try vertical. It shouldn't matter where you start with. So let's try vertical. Downward, negative 400, positive RA, negative 600, positive BV. And these two are horizontal, so ignoring that, and then equate to 0, please solve what's BV. Correct, it's 260. Correct, Pamela and Francisco, so correct Tamayo and Legado. So yeah, it's positive 260. So again, that's correct assumption for direction. And then finally, to solve for BH, that's just summation of forces horizontal equals 0. To the right 240. To the left BH. And then BH is obviously 240. Okay? And that is number 3. Any questions for number 3? Please answer in the chat. Okay, good. Next, let's answer number 4. Number 4. The beam shown in the figure is supported by a hinge at A and a roller on a 1 to 2 slope at B. Determine the resultant reactions at A and B. So now, take note, this is not components of reactions, this is resultant of reactions. So we're not looking for H and V, we're looking for the total reaction. So that's easy. Okay. First, let's identify our reactions. We have a pin here. So once again, you're gonna guess the directions. This is perpendicular and parallel to the surface. So perpendicular here, let's call that AV. And then horizontal here. And or parallel here, so let's call that AH. And next, we have this roller on an incline. Okay? That shouldn't be hard because we already know reaction of a roller is just perpendicular to the surface. This is the surface, so this is your reaction. Okay? And that's RB. Okay? Then, remember, whenever we're transferring slopes, if we have two perpendicular lines, the slope of the other is just the inverse. Okay? So therefore, the slope of this, okay? If here we have one as the vertical, now we have one as the horizontal, and then two as the vertical. And then compute for the hypotenuse, that's just square root of 5. Okay? So now you have your reactions. You're going to use your equilibrium equations to solve for the unknown. So once again, moment. You're going to choose where you want to take your moment. I'm going to choose B so that I don't have to deal with this reaction at B. So summation of moment at B equals 0. Let's begin. AH passes through B, so I'm going to ignore that. Next, AB. That's clockwise, so positive AB. Perpendicular distance is 3 plus 1, so 4. Next, 40. Counterclockwise, so negative 40. This times 1. RB passes through B. So ignoring that, equate to 0. From this, please solve what's AB. Correct, it's 10. Positive 10. Correct. Rafaela and Zaira. So pangalangan and multiplication. So it's just positive 10. Now that's not what we need. We need the total reaction at A. So meaning I need to find out what's AH. So to get AH, I'm going to use summation of forces horizontal. Okay? AH is to the right, so positive AH. There's a horizontal component to this force. Okay? So rather here, I'm gonna place the component here so that, it doesn't matter. Since we're not taking moment, the position of your component not matter. So I'll just put it here then. So let's call this the horizontal component of my reaction at B. So let's call that BH. And then this is the vertical. So this is BV. Okay? So now BH to the left. So negative BH. And BH again is just the horizontal component of B. So AH minus RB. Okay. Times the horizontal component, which is taking the horizontal side. So 1 over hypotenuse square root of 5. Then equate that to 0. Now there's one problem here, right? We have two unknowns, AH and RB. So I'm not going to solve for anything here. Okay, so I can't solve directly for AH. I need to solve for RB first. Okay, so let's delete that. And instead of doing summation of forces horizontal, let's do summation of forces vertical, since again, we have to solve for RB first. Okay, so vertical, we have AV as upward, 40 downward, and then BV upward. And again, BV is just the vertical component of RB. So plus RB, then get the vertical component. So that's vertical side over hypotenuse. Okay, there's no other force. So equate that to 0 and solve for RB. Since AV is 10. Correct, it's 33.54. Correct, Kenneth and Pamela. So De La Cruz and Tamayo. Now this is already the resultant reaction, right? So that's already your answer. Okay, we already solved for RB, not just BB and BH. And then now, since I know RB, store that. Then now you can use summation of forces horizontal. I recall our equation was AH minus RB times 1 over square root of 5. And again, RB is this, so please solve what's AH. It's positive 15. Correct, Michelle and Rafael. So probably it's positive 15. Then we're not done. We need to get RA. And RA, resultant, since we now know the components, is just AB squared plus AH squared. AH is 15, AB is 10. Please solve what's RA. Correct, it's 18.03. Correct, Marilyn and Kenneth. Abiosis. .03 unit kilonewton. And then to complete the answer, we also need to get the inclination. Okay, so this is actually your RA, right? And we want to know its inclination from the horizontal, theta. And we already know the equation for theta. That's just arctangent, vertical over horizontal. Please solve what's theta. Correct, 33.69. Correct, Zaira and Naomi. Correct, Ortiz and Mendoza. 33. And then direction. Our assumption for direction of reactions are upwards and to the right. So you can write up to the right or just an arrow. Okay. And there. That's your number 4. Any questions for number 4? Please answer in the chat. Okay, good. Since you don't have any questions, let's move on to number 5. The last question for non-concurrent force systems. Number 5. A pulley 4 feet in diameter and supporting a load 200 pounds is mounted at B on a horizontal beam as shown in the figure. So you have this beam, your pulley, which is 4 feet in diameter, is positioned here at pin B. Okay, and your pulley supports a load 200 pounds here, right? So the beam is supported by a hinge at A and rollers at C. Neglecting the weight of the beam, determine the reactions at A and C. Once again, we're looking for reactions at support. So we're looking for here. So we have a roller at C. That means, so let's draw a free body diagram. Okay, this is point C. We have a roller there, so there's only one reaction, which is perpendicular to the surface. So let's call this RC. And then we have a pin here. So perpendicular and parallel. So I'm gonna guess they're all upward. So let's call that AV, and then to the right, AH. Then let's draw the dimensions. So we have 4 feet. This is point A, B, C. So this is 4 feet, and this is also 4 feet. Yeah. Now what am I gonna do with this pulley, right? Now, if you remember the past topic for a moment, we had an example of a pulley system. Remember, when we got the summation of the resultant of that system of a pulley or forces acting on a pulley, we found out that it acts at the what? Can anybody tell me where does the resultant of forces on a pulley act on? In relation to the pulley, where does it act on? Anyone? Okay, from your topic for a moment, or I think resultant of concurrent force systems. Where does the forces or resultant of a pulley act on, or its location? Correct, Naomi, it's at the center. Very good. So remember, when you have a pulley, you can just take the resultant of the forces acting on it, and it's gonna be at the center. Okay? So let's say we have force here, right? We have a downward tension, and this is equal to 200. And then we have another one here. Let's write it this way instead. Okay. So we have a downward force here, which is 200. And then we have a force here. Since this is a pulley, it's the same as 200. It's always outward from the pulley. So this is 200. Get the resultant of that. And the resultant of that will act at part B or point B. This is your point B. It's going to act here. Okay. You can either draw it as an actual resultant. I think it's going to be like this. Or you can draw it as the components of your result. Okay. So I'm going to guess these are the directions of my resultant. So R, Y, and then X component of the resultant, Rx. So let's solve what's Ry and Rx. So let's solve it here. So Ry, again, just considering these two forces resultant on the pulley, okay, Ry is equal to, okay, we have a downward force here. That's the summation of forces y, right? So negative 200 plus 200. Now the question here is, what is the vertical component of this? Now take note, this is at an angle 60. Okay, we do alternating interior angles. If this is 60, then this is also 60, right? This is 90 degrees. So to get the angle from the horizontal, that's just 90 minus 60. Therefore, this is actually 30 degrees. Okay, so this is 30, getting the vertical component. So that's sine 30. Please solve what's Ry. Correct. It's negative 100. So correct, Matthew and Ryan or Simon. Puchero, Anilon. Again, sign is important. Now, in this case, the negative sign does not denote whether my assumption is correct or not. It actually shows the direction of the resultant. So meaning RY is 100 pounds downward. Okay, so this is correct. RY is downward. Next, RX. Summation of forces X. So this is to the left. So negative 200 X component. So that's cosine theta. This doesn't have a horizontal component. So please solve what's Rx. Correct. It's negative. Correct, Jaiser and Matthew de la Cruz. It's negative 173.21, and that just means it's 173.21 pounds to the left. Okay, then store that value. And so again, Rx to the left. Okay, so again, the signs of your resultant just indicate its actual direction. All right, so now we have this free body diagram. I can finally solve for the unknown. So let's begin. Okay, so the goal is to get reaction at C and A. So if I take moment at A, I can solve for reaction at C. Okay, AH and AV pass through A. So ignoring that, Rx also passes through A. Ignoring that, Ry rotate about A clockwise. So Ry times distance 4. Next, Rc, that's counterclockwise, so negative Rc, distance 8. Ry again is this, we solve what's Rc. Correct, Marilyn and Colin. So Pere and Collins. Positive 50. Okay, so that's already your answer, 50 unit pounds. Next, solving for AV and AH, and then finally getting the resultant of that. So we can start with summation of forces vertical or horizontal. Let's try summation of forces horizontal. Okay, AH to the right, so positive AH, Rx to the left, negative Rx equals 0. And obviously, from this, AH is 173.21 pounds. And we're not done. And then solve for AV. Okay, so positive AV minus RY plus RC equals 0. Please solve what's AV. Correct, Joshua and Eman. So Bongalos and Santones. Okay, and now from this, we can finally solve for RA, which is AV squared plus AH squared. Please solve what's RA. correct. It's 180.28. Correct, Dreiser and Joshua. De La Cruz and Bongales. Unit pounds. And then to complete the answer, also solve for theta. It's arctangent. AV over AH. Please solve what's theta. Correct. Colin and Naomi. And also, 2 points pa niya. And then Rain Simone. 16.10 degrees. And then check. AH to the right, AV upward. So upwards to the right. And that is the answer for number 5. Any questions for number 5? Please answer in the chat. Since you don't have any questions, that ends the topic for equilibrium of non-concurrent force systems.